The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thanks for joining us for another episode of our MecSoft's monthly AMS webinar training series. My name is Don LaCourse. I'm a senior application engineer here with MecSoft Corporation. And normally we have more than one organizer and presenter, but today I'm going solo. So bear with me, and also as we go through the webinar, if you have any questions, please feel free to add them to your questions panel. If I don't get to them during the webinar, we'll certainly email you after the webinar. Okay, so what's our topic? This month we're going to talk about control geometry and the effective use thereof in 2 and 3-axis machining. Now, the key word here is control. So everything that we talk about today is going to be towards controlling your toolpath operations, the paths themselves. Okay, so let's go ahead and get started here. Again, some housekeeping. If you have any questions, go ahead and put them in the questions panel. I can see the questions here on my end, and I will answer them as we go out through the webinar, and we'll also have a chance at the end for question and answers. Also, this webinar is being recorded, and once we process it and clean it up, we will send that out to you after the webinar, maybe in a day or two. Okay, let's keep going. Okay, what's our agenda today? Control geometry. What is control geometry? We're going to cover that, as well as what it is, what does it mean to you in 2.5 and 3-axis machining. We're going to talk about how 2.5-axis control geometry drives your toolpaths, and how 3-axis control geometry contains your toolpaths. So those are two different, control geometry is used in two different ways in 2.5-axis and 3-axis methods. We're also going to talk about the most common cutting tools and how those tools are compensated for in the toolpath based on your control geometry. We're also going to talk about stock allowance. You need to understand that control geometry is not just what you select in your control geometry tab of your operation dialog. All geometry on your screen, it can be considered control geometry, whether it's the stock box or however you have your stock defined, stock from selection, stock from extrusion, whichever, as well as all visible surfaces on your screen at the time that you regenerate your toolpath. And we're going to talk about some tips for calculating 3-axis control geometry. And we're going to use talk about how reference surfaces are used to affect 3-axis toolpaths. So basically, you can add geometry to your model for the sole purpose of directing or controlling or guiding your toolpath. These are surfaces that you turn on visibly when you generate and then turn off again when you're done. Okay, let's move on. The key benefits, obviously, of control geometry. It helps maintain machining accuracy, and you may wonder, well, how am I changing my accuracy just by selecting my control geometry? Well, we're going to talk about that, and we're going to tell you when we get to the reviewing the most common tool types. The selection of the tool and the control geometry can have effect on your accuracy, and I'm going to talk about that in just a minute. Also, obviously, the more you can contain your toolpaths, the more you can minimize machining time. So you don't want your toolpaths recutting air. You don't want them going into areas where you don't need to go. You don't need to cut anything that is not essential. And also, control geometry, it helps to facilitate a more effective toolpath coverage, and we'll talk about that as well. Okay, first up, we're going to talk about how is control geometry, what is it, how is it used for both 2.5 and 3 axis? What's required, what's not required? So if we look on the left, we see a 2.5 axis example. If you look at the top, you have some curve geometry. Curves are required for 2.5 axis machining. If you don't, obviously, if you don't have any geometry, you can't do any machining. But in 2.5 axis, you only have to have curve geometry, and that will guide your tool path. Now, if you do have a 3-axis model or a 3D model, that's great. You can use the curves or face edges directly from the model to control your tool paths. And we're going to talk about that a little bit more in just a moment also. On the right, when you look at 3-axis, surfaces are required for 3-axis operations. You cannot perform, if you try to perform a 3-axis operation with no geometry and no surface geometry, it'll tell you you can't do it because you don't have any geometry. So you got to have surfaces. It can be one surface, and we've got a great example of that we're going to show you in a moment, or it can be a completely closed 3D solid model, whichever, but you have to have surfaces. And in 3-axis, the curves are actually optional. You can use your control geometry selections to contain your 3-axis toolpaths. And I want to stop here and mention that you may think that, well, control geometry, this is a really basic, topic, and reserved just for new people or somebody that doesn't know how to use the program. That's not the case. Your control geometry, and we're going to show you some real world examples where the control geometry directly affects very complex toolpath operations. So it's not just something you need to learn at the beginning and then forget about. This is something that you learn and you develop your own style, your own types of geometry as you move forward. Okay, let's go to the next screen. Okay, I mentioned tool geometry and how it's compensated for. We have 4 of the most basic or most used tool types in MecSoft CAM's plugins. And the little dots you see on the screen, those are just references that let you know what areas of the tool are being applied for any given piece of geometry, control geometry. And then also listed is the most common tool operation types that uses tool types. So let's start on the left. The flat mill, most common tool type ever used. It's primarily used, however, just for 2.5 axis operations, and for some 3-axis roughing and re-roughing, and for clearing flat areas, obviously. So under 2.5 axis, all the roughing, re-roughing, facing, slotting, pocketing, profiling, hole pocketing, hole profiling are all used with the flat end mill. Not that you can't use the round ball mill, but there's special considerations. So let's move over to the ball mill. As you can see in the ball mill, the 3 dots, they cover the tip of the tool, and it rides up around the radius here to the full diameter of the tool, and then also the flute length of the tool. This area between the tip and the full diameter is the area that you need to be careful on. And we're going to show you and talk about that a little bit more, because as the ball mill touches your control geometry and you move in Z, obviously this ball is going to ride over your control geometry. So in 3 axis, the ball mill is the most common tool used. You can use it for roughing, and you can use it for finishing. Obviously, you can use it for pre-finishing. So we have roughing listed, parallel, radial, and spiral finishing. Typically use the ball mill. Other operation types: projection pocketing, 3D offset pocketing. These are the more advanced 3-axis advanced tool paths. And then, excuse me, and then it is also used for pencil tracing, valley, machining, etc. So let's move over to the V-mill. The last two tool types, the V-mill and the chamfer mill, are considered specialty tools. So you only use them in certain types of operations. Obviously, in 2.5 axis, if you have a tapered mill, a V-mill, you will use that for any chamfering operation, any V-carving operation, but also engraving. And that's a toolpath that we're going to talk a little bit more about. And we're going to show you real-world examples of that. In engraving, the tip of the tool follows your control geometry exactly. So you can even go so far, and we got an example of this as well, you can even go so far as to draw your toolpath curves and use engraving to make your tool follow that path exactly, and it won't deviate from that path. So if you want precise control over your tool, you can use the engraving operation, and you can use any tool with the engraving operation, and the tip of the tool will follow the engraved tool path. Just 1 second. I have to take a drink of water. Okay, so we covered all of the tools. So you just need to understand that whichever tool you use, the flute area, starting from the tip, going around to the full diameter, all the way up to the flute length, these areas of geometry on the tool are compensated for in relation to your control geometry. So it'll, obviously your tool paths are going to compensate for the tool diameter. Okay, let's keep going. Let's talk about 2.5 axis stock. Now I mentioned previously that stock is also a control geometry. Obviously, when you define what your stock is, that is what's being cut. That is what's being calculated to remove material in the application. But stock is compensated for different ways in 2.5 axis versus 3 axis. Here we're seeing a typical 2.5 axis part. We're cutting in levels. You guys might have recognized this part. We're going to show it again on the next slide. Basically, in 2.5 axis, you're moving in X and Y with the Z axis fixed at a certain depth. So when you set the, over here on the left, if you look at we've got an example dialog, 2.5 axis pocketing, and that's the operation that we're doing that you see in the middle here. You can define your stock, and we have it defined of 0.1. Well, 0.1 for 2.5 axis stock allowance is only calculated on the X and Y directions of your control geometry. So if you're looking down on the part, as the tool moves in X and Y, this stock is being compensated for at your control geometry. And the stock can be a positive or a negative. Obviously, if you're going to come back with another finishing operation, you're going to want to leave a positive value for stock. The tool will, stay off of the control geometry of that amount, but you can also put a negative stock, and you can overcut your geometry. And that's used also in many applications. Inlays is one example where you've got thin, small pieces of inlay material, whether it's pearl or other types of wood, where your geometry, control geometry, can be the same for both the pocket and the profile. And you can just use your stock allowance to control the exact tolerancing of your cut. So over here on the right screen, we're talking about we're showing the cut levels tab. Cut parameters tab, you control the XY stock allowance. Cut levels tab is where you control the Z depth. If you want to leave some stock allowance in your Z depths, you can use the cut levels tab to divide your total cut depth into both a rough depth and a finish depth. So you can leave some finishing stock at the bottom of your cut levels. Okay, so anybody have any questions about you know, what we're looking at here on any of these slides, please ask. And you can also ask a question during the webinar. You can go to our website and you can chat with us and ask a question. We also have a web form on our website where you can ask questions. And also, obviously, you can call us directly and ask for tech support and get your questions answered as well. Okay, so let's look at how stock is allowed for in 3-axis. So in 3-axis, you have roughing and finishing operations. In typical horizontal roughing 3-axis operations, you have a stock value here on the cut perimeters tab. We have, in our example, we have it set to 0.1. And in the example here, you can see that 0.1 is calculated at the closest point of your step level to your actual part surface. So if you set it to 0.1, the cutter's not going to get any closer than 0.1 to your part based on your intolerance and out tolerance. And then also I wanted to mention here, there's an option in horizontal roughing to use a clear flats option. When you enable that, the stock allowance is not going to apply. You're going to clear that flat as a finishing pass. So everything on the tapered sidewalls, everything but the flat areas will leave stock. Flat areas with clear flats enabled, you're telling the system to clear that flat area as a finishing pass. Now let's look over on 3-axis finishing. Obviously, the same applies. For a stock allowance of 0.1, it's going to leave no more, no less than 0.1 of stock material away from your part based on your intolerance and your out tolerance. And again, since you cleared flats in the roughing, obviously, you're not going to have any cutting or recutting on the flat areas. So let's move on. Okay, what we've decided to do for this webinar is, we could have come up with some basic examples and showed you how the geometry affects your toolpath, but we thought it best to take some real world examples. And some of them are simple, some of them are complex. But what we're going to do is we're going to look at these examples and we're going to see how this particular user used the control geometry to affect their toolpaths. And this part, we want to give a shout out to Advanced Robotic Technology in Queensland, Australia, for providing this part for us to showcase and evaluate. Okay, so what are the type of features we got on this part? We got the bottom shown and we got the top shown. We have fillets. This is a common concern when you have a fillet on your part and it goes around. How are you going to cut that fillet? How are you going to contain it? Just that fillet. And this is a relatively complex fillet because it goes all the way around, but it also mates here at the front and then squeezes around on the backside. So we're going to look at that. And at the bottom, obviously, we have 2.5-axis pockets going on at different depths. And then we have some contoured surfaces that the user used 3-axis roughing and finishing pass there. And we're going to show you this part in a moment. Let's go to the next one. Okay, this is a really interesting part. This is provided by Dingwall Guitars in Saskatoon, Canada. And Dingwall is a major player in electric bass guitars around the world. And the guitar you see here is called the D-Rock model. And this guitar is machined using only one surface. And the rest is 2D curves. And since you don't have any closed surfaces, not a solid model or anything, you won't see the actual part until you simulate the toolpaths. So what we're looking at is the final cut material simulation. We have a stock from extrusion. So we got one profile curve around the entire part defined as a stock by extrusion. We have some pocketing, profiling, and engraving going on here in the neck area where the neck attaches to the body. I mentioned previously that users use engraving to control exactly where the tool path goes, where the tool goes, and this is one example. And we got 2.5 axis pocketing going on, more pocketing here. We got 2.5 axis engraving where we got some contoured edges here, and there's another contoured edge up here. You can see it a little bit. And then we have 3-axis roughing and finishing. So let's move on to the next example. This is an example provided by Hancock Central School in Hancock, Michigan. They have a complete foundry, steel foundry in the shop where the students can mold medallions out of poured aluminum. And then they take those stock medallions and the stock blanks of the medallion, and then put it on the mill and actually carve out the rest of the medallion. So here we have, just one moment. Here, up here on the left, we have 3-axis horizontal roughing, parallel finishing. This graphic or the raised area you see in the middle of the Predator logo was generated from our art module. Our art, I'll just mention just briefly that in the art module, you can take a 2D curve drawing and you can raise it up in the Z-axis to give it depth. So in this example, we just had the curved geometry of the Predator logo and then used the art module to create a 3-dimensional mesh. And then this is a Visual CAD example. In Visual CAD, we then added obviously the lettering, and the cylinder as well, located at the base of the mesh. So we got 3-axis roughing, finishing, we got lettering, 1/8-inch high lettering above the base surface here. And then we have some profiling and chamfering going on at different places. And we're going to be looking at this part as well. So the next part. Now, this obviously is a cavity insert block of a plastic injection mold. This is courtesy of Connolly Manufacturing in Sterling Heights, Michigan. If everyone's aware of Sterling Heights, that's where all the automotive tool and die shops are, and Connolly obviously is one of them. This example obviously is not an automotive example, but just a really good example of how you can use control geometry to control your cutter, specifically for mold applications. You have extra care applied to how that tool cuts your parting lines. And we're going to show you not only the control geometry, but also some external reference geometry used to also control the tool paths at the parting lines and really about all of the surfaces that we're cutting. Okay. So this is the demo portion. We're going to go through all of the parts that we just mentioned. We're going to show you the actual real world parts. So give me just one moment. Okay, hope everyone can see that. This is the component, the first component we looked at from Advanced Robotic Technology. This is a prototype component used on one of their 8-axis robots. So it's a solid model in Rhino CAM. It's from aluminum. And as you can see, there's not just a part there, but it's also a lot of geometry, 2D curves and whatnot. And these 2D curves are the control geometry that is used to control the various operations. So let's look at this from a top view. Okay. So we got curves, obviously, at the edges of the solid. We got curves that are offset from that. We got curves outlining the different pocketing operations, and these are used to actually guide and control the cutter while it's making these operations. And then we also have a cover with control geometry based on the perimeter curves of the part and also offset out from the part. Okay, so let's look at some of the toolpaths. Okay, let's start at the top here. So we got a machining operation set with a group of operations, and this is just applied to the cover. So in this example, pretty basic, the perimeter of the pocket is used as a control geometry to cut that material out. And then for finishing, also the same outer perimeter is used. One thing that's interesting to note here is that you notice that the toolpath doesn't go all the way to the top. You can control your toolpath in the Z. A ball mill, again, was used for finishing. And consider that ball mill, okay? When that ball mill comes up and touches your control geometry, you don't need to cut any further than that. So in the Z-axis, we just put a containment height calculated for the depth of the ball, and the toolpath stayed at that height and didn't need to go any further. Okay, so let's go down here. So this, the stock model for this is a box stock, the same width as a part, and obviously wide enough to encompass the part. But you don't want to cut all the stock material, so we're using control geometry. In this case, three-dimensional geometry. We've got the perimeter edge here being used, and then we got some added geometry out in front just to get this front area cleared out. But we also have on the back side, the control geometry goes down around the perimeter of the part. And that's one thing to understand in control geometry. It doesn't have to be just 2D geometry. It doesn't have to be just a square or a box, or a circle or whatever on the XY plane. You can select the edges of your surfaces wherever they are, and they will internally, the algorithm will project those flat and use that perimeter to calculate the tool paths. Just one second. So here we got some parallel finishing going on for these pockets that have contoured surfaces, and they're just using 2D curves, rectangles, or 2D profiles to control those cutting areas. In here in the finishing, again, similar to the roughing, we're using the same control geometry. And again, the cutter is not coming all the way up to the top, only because it's a ball mill. And if you go up when your ball mill comes up and the tangent touches your control geometry, if you keep going further, you're recutting this edge. So every time you go up to this edge, the ball will roll it'll roll on it till the tip of the tool actually touches this edge, which means that you're degrading this edge every time that ball moves from one point to another on the same edge. So we contained it in the Z-axis and also contained it around the front here. In these examples, we've loosened up the step overs so you can see the tool path. Obviously, in their production parts, the step overs are much closer and more dense to get a better surface finish. Okay, let's look at some more pocketing. Again, we just have a two-dimensional profile for the perimeter of the pocket, and the pocketing operation controls the Z depth and the cut levels. And here's another example here. This is an interesting example only because, excuse me, your control geometry is not on the part, and you will run into this in special situations where you can't use the edge of the part, or the edge of the part doesn't condone itself well to controlling the perimeter. So you can project your perimeter curves up to a plane, or you can just draw your perimeter curves on any XY plane, and it'll be used and projected down to create the tool path. So the control geometry is up here on your cut levels tab. Let's just look at that real quick. Your cut levels tab. You see here that the location of cut geometry is not at the top, it's not at the bottom. We're telling it where it's at. We're picking the top, okay? We're using this as a control geometry, and you're telling this is where we're going to start, this dimension in Z, and these are our cut depths, finish depths, etc. And also we have some additional pocketing going on for all these different areas. Engraving, this is another interesting use of engraving. You only, like I mentioned before, you only need a curve to engrave, and the tool, which is a 5mm end mill, is just going to follow this curve. It's going to follow that curve at a particular depth, and that's all that is needed for that operation. So we got some more pocketing, and we got some horizontal roughing going on for these additional pockets, drilling or more pocketing on this trough here, and we're just using the edge of this trough, but extending it out here to get complete coverage through this opening. And then obviously the opening here, they're using the perimeter for a pocketing operation. Let's see what else we got here. Okay, this is an interesting one. We're going to flip the part over, and we're going to look at this cover. You will run into this, and many of you may already have run into this, where you've got a three-dimensional contoured part, and you put a three-axis parallel finishing path on that part, and then you realize I'm not getting full coverage. Why is the tool not going all the way down? I mean, I got to cut the whole part. So what's going on here? Well, if you recall, when we talked about the different tool types, the ball mill, this is the effect of the ball mill. And three-axis, and most all of the three-axis operations, the tip of the tool is used to calculate the tool path, where the tip of the tool is projected down onto the surface to calculate your path. And if you look at this on the end, let's see if we can get a good view of this. So your ball mill is coming around, and we could simulate it, but I don't want to tax. We got a lot of parts loaded up, so I don't want to tax the system too much. So with the ball mill, as it comes over this edge, the tip of the tool, when it lines up with the edge of your control geometry, that's it. I mean, your control, you're telling it. The control geometry is right here. In three-axis, the tip of the tool is used, and virtually all of the finishing, three-axis finishing. So when that tool ball comes around, the tool tip projects down and touches your curve, it stops. So that's what happens. That's why you get that. So how do you compensate for that? So what you do is you offset your control geometry. In this path, we're using the edge of the part. And this path, we're extending that edge out. So we're using the same edge of the part on the end. We're extending it out further on each side. And what that does is it allows the tool to come all the way down onto the part. Okay. And also, let's see, we got some control surfaces there. A control surface just to ensure that the cutter doesn't go any further than that. Okay, So let's look at a few more operations. Go a little bit quick because we got a lot of parts to look at. Here, we was talking about filleting. Let's look at the top view. Actually, the bottom view. Okay. So we want to fillet that edge. So we're using see what operation type that is? They're using a horizontal finishing operation. Okay. And they're just containing it with an offset curve all the way around. But you will notice if you look into the isometric view on the other side, this is used for the toolpath. You can't see it very well, but also the top edge is used in the perimeter. So the horizontal finishing, in that operation, the Z depths are contained, so it doesn't go any further down than the tangent and no further up than this top edge in these areas, and then it goes all the way up here. So this is the way you would machine a fillet. One way, of course, you could do it with a fillet mill. If you had a fillet mill, you could, run the fillet mill in a 2-axis profiling operation around the edge. But if you have a ball mill, this is the way you can do it using 3-axis horizontal finishing. So again, we got pocketing there, and we've got some hole pocketing there. Okay, let's go to our next part. I'll make sure we get through all of these. So the next step was the D-Rock. I mentioned that all they used was one surface. So this is a surface, okay? It's one extruded surface, and the control geometry is just 2D curves on the XY plane. The stock is a stock from extrusion. So they're taking the perimeter curve, extruding it down, and that's the stock definition. So what's interesting about this, let's go back into this. So let's look at the operations. We have some engraving, okay? So they've got curves that they drew to exactly position the tapered V-mill to engrave these areas. If you remember in the, when you go back and watch the video, if you go back to the slide where we showed this, you'll see that there was an engraving bevel here, some engraving in the front areas. So this is how they controlled that. They knew exactly where the tool needed to go. They drew the curve, and they used an engraving operation. And then we use from roughing, obviously. This is a 3-axis contoured face, so you can see the horizontal roughing going on, and we've got roughing on the other side, and we got parallel finishing across the entire contoured surface. And then we've got the perimeter profile, and let's just go down these real quick. So we got pocketing for the bridge, and all, again, they're just using the flat 2D geometry on the XY plane, and they're controlling the depths within the dialogues of the pocketing operations. So we got another pocketing there. Here's where I mentioned that they drew their curves exactly how they wanted the cutter to follow. And if you look down here, we've got some profiling, and then we got pocketing. So what they're doing is they're using the engraving operation, and they drew the curves they wanted the tool to follow exactly, and that's what it's doing. Okay, so let's go on down here real quick. We got some cleanup profiles. We got some cleanup profiles there, a little bit more pocketing. Then we got some other operations here on the bridge, etc. So this is a cool example of you only have one surface, you have 2D curves, and you can create a final product, all of the toolpath operations you need. Okay, let's keep going here. We're going to go to Hancock High School. This is another interesting one. So I mentioned that, again, if you guys have any questions, put them in the questions panel, and we'll get them answered towards the end of the webinar. Okay, so we've got a the logo here in the middle, and that was created, like I mentioned before, we're using the art module. So we got a logo in the middle, we got other geometry there for the lettering, etc. Let's look at the toolpaths. Turn them on. So we got horizontal roughing. All that's needed is the perimeter curve, circular curve around it. And then we have some horizontal roughing. Now, horizontal roughing to clean this out around this lettering, okay? Let's keep going to look at the finishing. This is just a parallel finish using the perimeter curve of the logo. And then we got some additional finishing that follows an offset curve from that edge. So if we turn this off, you see we got two, this is the inner curve and this is the outer curve. And we're just finishing off in these areas. And then more pocketing going on here. And you can't see them because the pocketing actually extends. Let's turn them on. The pocketing extends below the surface here. So we're pocketing out this area. And then we're doing additional profiling to get a shelf on the end. And then also, I mentioned the lettering. Now they're using profiling to do the lettering. There are alternate ways of doing it. You could do the lettering with a horizontal finishing operation, which would only cut the perimeter areas and the finishing path. You can use that. One good thing about using the profiling is you have more cornering options. You can control how the ball or the flat mill, how it travels around, how it behaves at each of the corners, where you can get a more accurate, sharp corner using profiling versus horizontal finishing, which in finishing, obviously, if you get one or two passes, you're cutting multiple times around that lettering. So you could, depending on your tolerances versus, your stock tolerances, your part tolerances, your tool itself has tolerances, so they can build up internally and actually degrade these edges. So you need to be careful and take a look at how you're going to do those letters. And here's some more facing on the top of the letters, just to flatten those off. And we've got some profiling on the outside, some more chamfering to chamfer these edges, more chamfering here, more chamfering there. Okay. So that's how you can use control geometry basically to control all of the operations in this medallion. Okay, let's see what else we got left. We got another nice one here I want to show you. Connolly Manufacturing. Okay, this is the cavity insert block that we showed on the slide in the presentation. And we got a lot of operations. We're not going to go into a whole lot of detail of the operations, but I do want to show you the control geometry and some additional geometry that we used, they used to control the toolpaths in some certain critical areas. So we've got over here on our layers, we got a number of layers called guide 1, 2, 3, all the way up to guide 7. And these are different additional surfaces that they turn on or off to mask certain areas of the part. So let's look at some of the operations. Obviously, we got just a facing operation. The base of the part is used, the perimeter of the base is used to control that. Again, profiling, excuse me, excuse me. Again, the profiling based on the bottom perimeter of the part. So here, if you look at this operation, the name of the operation we have with guide 1 and 4. So when this horizontal roughing is calculated, they turn on guide number 1, and guide number 4. So what that does for them is it masks off all of the areas that they don't want to machine. Obviously, it's erupting. They don't want to erupt down in the cavity because we're going to do that. They're doing it separately, so they don't need to rough it out initially. And these surfaces may look complicated, but if you're aware or obviously familiar with Rhino CAM, in Rhino, modeling tools in Rhino are superior to virtually any other CAD program. I mean, it's very easy to draw these additional surfaces, whether they're revolved, extruded, or matched, whatever, however they created them. So with those two layers on, they did the roughing, the horizontal roughing. So now they did the same surfaces on, they did a re-roughing. So they did a roughing and then they did a re-roughing. And again, the bottom perimeter of the mold of the insert block is used to contain the tool path. So again, with the same layers 1 and 4 surfaces turned on, they did some pre-finishing of the insert, the parting surface of the insert block. And again, they're just going right over the cavity area just to get a good parting surface finish. And here's another one, another pre-finishing operation on this same area, but it's contained, in this case, it's contained to this edge of the cavity or the insert block parting surface. Okay, so this is the parting plane, this is the actual parting surface. So let's go on further. This roughing operation is for the cavity. So they have these turned off and they have guide number 7 turned on. And let's turn off the toolpath. So what they did here is, if any of you are mold machinists or tool and die machinists, you understand the value of the parting line. The parting line is sacred. The parting line should only be cut once. When you cut a finishing pass, you only want to cut that parting line and a finishing pass one time. If you're using a ball mill, you don't want the ball mill to roll over the parting line edge, because again, as it rolls over, it's cutting that edge again and again, and you don't want that because you'll get degradation of the parting line. So what they did here, they just took these cavity edges and extruded a surface upward, okay, which sheltered the parting line. So then they put in a roughing operation, which calculated the roughing operation in the cavity with this surface on. So the tool doesn't get near the parting edge. It goes all the way up to the top of this extra surface they have in there. So here again, we have another, that was a roughing, a re-roughing. This is another re-roughing just to get some more material out of the cavity. And some additional re-roughing, and this one they have guide number 3 on. So let's turn these off and put guide number 3, and let's see what they're doing with that. So let's turn the toolpath off. This is an interesting, very interesting situation. You can use this. Well, I'm not going to call it a trick, but it's just a way of using surfaces to guide your toolpath in such a way that you're guiding it as it moves over this parting line. So we have an interior island, we have a parting surface in that island, we have a shutoff parting line right here at this edge. And on this particular operation, let's get this displayed for a second. We got about 10 minutes left, so we're going to wrap this up in about 5 minutes, and we'll do some questions and see how it goes. Okay, so they got a horizontal re-roughing, and they're selecting these surfaces as the control geometry. And when you select surfaces as control geometry, you have these additional controls where you can control how the cutter behaves at the edge of the surface. So in this case, we're telling it to go past the edge. And then with this guide surface on, the tool is going to rebuff it out, and it's going to go straight out onto this edge because it's going past the edge and it's staying on this surface. So it doesn't roll over the edge, doesn't go into the cavity. So that's an important use of not only the control geometry and the end condition, but also a extra guide surface that we put in there. So let's look at this one. Again, this is a finishing operation with 1 and 4 on. Let's go ahead and put 1 and 4. And this is a another finishing operation for the parting surface area, not the cavity. And you'll see that the end condition again was set to pass. And they're using these surfaces, all these surfaces here as the control geometry. So the tool travels past the edge, a width of the tool, and it can't go in the cavity because you have this surface turned on. With that surface turned on, obviously, it would roll over and go into the cavity, so they don't want that. So it's a good way of using extra surfaces to guide your toolpath in critical areas. So let's keep going. This that was a finishing going in the X. This is a finish going in the Y. And again, this is some more finishing. Let's go to guide number 3 again, where same as the roughing operation. And again, we made the step overs a lot larger than they used, obviously, for finishing, but this is so you can see the toolpath better. So with that surface selected, again, with the end condition set to pass, the finishing operation hits the parting edge, continues on past for the width of the tool, and it stays on your extra surface, guide surface you put in there. So this, it adheres to the rule of a mold maker, of a proudly, I'm an old mold maker, old as in I did it a long time ago for a few years. And as a mold maker, anything you can do to protect your parting line, you can, because as a mold maker, when you supply parts for first piece inspection, that's the first thing they're going to look at is your parting line. If you got a nice, tight, clean parting line, that's representative of a quality mold shop. So this is just one tool that you can use to affect that quality and accuracy at your parting line. So let's go on through these real quick again. I want to make room for some questions here. So we got some finishing going in X, finishing going in Y, same end condition, the same extension, etc. And then we get into the actual cavity. So let's turn this off and put on number 7. Again, this is this surface that they added. They extruded the parting line up so that when they start cutting the finishing passes on the cavity, you'll see that it just goes right past the parting line on up and over the surface. And you'll see the rolling that I'm talking about right here. When you use a ball mill, as it gets to that edge, it's going to roll over it because the tip of the tool is being used to calculate the tool path. So at the end of this path, the tip of the tool is on this top edge of this surface. Okay, so it's rolling over on top of the surface. Now, if this was down here, you would have major degradation of the parting line. I mean, we've done previous webinars where we went into this in a lot of detail and actually did the simulations both with and without these guide surfaces, and you can clearly see the degradation of the parting line difference. What I'll do is I'll put a link in this description of this video when it goes out to the other video where we talked about this in a lot of detail. So we have the finishing operation, a pre-finishing. We got another finishing, and then we have some additional cleanup in this one area here. Basically used a curve going from here around. And what I didn't mention too, the control geometry for the cavity machining was the top edge of this extended surface. It's not down here. The control geometry is up top. And then move on past, we got extra cleanup there, extra cleanup here, and then extra pencil tracing to clean up this edge. And again, this is with 1 and 4 on. So it cleans up this edge right here using these perimeter curves and some additional curve machining. Let's see, turn 1 and 4 on. 1 and 4. Okay. Some additional curve machining here along these edges. Okay, this I hope gave some real world examples of how people are using control geometry to control and affect their tool paths, not only for roughing, not only in 2-axis, but also in 3-axis, and 3-axis roughing and 3-axis finishing. Okay, we're about 5 minutes out, so I'm going to go back to the slide presentation, and we're going to open this up for questions. Again, if anybody got any questions, please put them in the questions panel and we'll get to them. We can answer the questions right now. And I see one question there, a user asking, how do I know what to select for control geometry? We've given you a lot of examples, but you still may be wondering, how do I know what to select? How do I know? Well, obviously you can practice trial and error, selecting different things and see what the toolpath, how it comes out. But also there's some basic guidance for 2-axis versus 3-axis, and we went over those in a previous slide. For 2-axis, obviously, you're going to be using curves or surface edges, 2-dimensional curves. So in 2-axis, the curves that you select is going to contain the toolpath. It's a pocketing operation. The curve, the tool is going to go up to that edge. Obviously, if there's stock, it's going to back off that edge by the stock amount. For 3-axis, just remember that anything that's visible when you perform a 3-axis operation is going to be calculated. So you can use that to your advantage. Not only are you cutting your 3-dimensional surfaces of your part that you want to cut, but you can put some extra surfaces in there and affect the way the toolpath is generated. Okay, so, and again, if you use curves in 3-axis, those will contain the toolpath. So if you've got a relatively complex 3-dimensional part, you can do the roughing, you can do the finishing. You don't really need to select anything for those two, and it'll just machine the entire part. But in most cases, you don't want to machine the entire part, or you might want to remachine just a certain part of the part. So that's where you select additional geometry, either surface edges or curves, and that will contain the toolpath up to and onto the curves that you select. Okay, let's see if you got any more questions. Add them in the questions panel. We've got maybe 1 minute left. Let's go ahead and leave it open for anyone that has any questions. Again, we're going to make this video available. And as we discussed about, the question, well, how do I know what to use? I'm going to put together a little matrix, and I'll make that available to you, which will tell you on each operation type what is the typical geometry that's selected for that operation type, okay? For example, if it's for profile, 2.5 axis profiling, obviously you're going to select a profile and the tool will follow it. If it's a facing, then you're going to select the boundary area where you want the face mill to travel, and in facing, the center tip of the tool goes to the edge. So there's different containments. And I'll put that matrix together, and I will put a link in the video. So if you check back in the video, that'll be available to you. Okay, if there's any more questions, I don't see any more questions. So you guys take these examples, real world examples that we went through, apply them to your specific geometry, and hopefully you can walk away with some ideas and some tips to greatly affect your accuracy and surface finish on your parts. Take care and have a nice day.